Let's take a moment and think about the scale that we're talking about when we come all the way down to the acid, especially for the proton. Now, when we have a hydrogen atom, and here I'm talking about neutral hydrogen atom, that's going to be one proton and one electron. Now on that scale, the electron was hanging out somewhere in this space of 10 to the minus 10 meters, while the nucleus was on the scale of about 10 to the negative 14 meters. So 4 orders of magnitude smaller. That's 1 with 4 zeros. That's 10,000 times smaller than an atom, right? And that's the visual that I often like to bring up, where if you visualize a football arena, about 100 meters long, 100 meters wide, and about 100 meters tall, and it was roughly spherically shaped, in the center of that field would be sitting a marble. That marble would be your nucleus. Zipping around that big stadium is going to be a fruit fly, and that is going to be the electron, and it's moving at close to the speed of light. But what happens when you take that electron away? Now all you've got left behind is that marble. And it's going to be a very tiny particle with a full size plus charge. And so it's going to be really tiny with a full charge. It's going to be really easy for it to stick to a water molecule. Now, let's just think through what's going on there. We're going to have, actually let me draw it a little bit more 3D. We're going to have our orbitals that have lone pairs sticking off of the oxygen. We're going to have our hydrogen sticking down like this. Now over on this side, we've got a partial positive charge and a partial negative charge, partial positive, partial negative, and our polar arrow is pointing this direction. Now if an H plus comes along, keep in mind that it's going to be a tiny speck, smaller than that dot on this scale, 10,000 times smaller than the oxygen atom, right? Well, it sees a giant pile of electrons. It can just kind of sneak in and just stick into that little gap there. And it's inside that cloud of negative charge. So it's going to be really easy for us to end up getting an H3O plus ion. And that's why we've had to memorize the hydronium ion way back. Now, if I take hydrochloric acid, hydrogen chloride, it's a gas. That's why I just described it as hydrogen chloride. We use the covalent name for it. Now that it's in the water, though, it's going to dissolve and dissociate into H plus and Cl minus. Once it's in water, we call it hydrochloric acid, and we'll see the nomenclature in another video, but I want to make sure that I tie it in here. Now, hydrochloric acid, when dissociated, gives me the H plus ion, so the hydronium ion, and the chloride ion. Now, hydronium ion is just a proton, like I just pointed out up above, right? And so the other way that we'll often write that, there's no way it's going to stay in a solution of water as this tiny little particle with a full-size charge and never bother sticking to that orbital of electrons. It's not going to happen. It will stick to one of those water molecules in solution. And guess what? There's so many of these water molecules in solution, it is definitely an excess reagent, right? And so we can also describe the end game as being H3O plus aqueous and Cl minus aqueous, the hydronium ion and chloride ion. So either way is totally fine. Sometimes you'll see people write that there's H plus. Sometimes you'll see people write that it's H3O plus. And they're both saying the exact same thing. We're talking about a single proton that popped off of an acid and is sitting around in water. So both those things are going to be completely equivalent whenever we're talking about acids. It's just that you have to make sure that you balance your chemical reaction by showing water if you want to have the hydronium ion. That's going to matter a lot when you do equilibrium issues in Chem 2, and it's going to matter quite a bit in Chemistry 1 as well, so make sure that you get polished at doing it one way or the other and doing it deliberately each time that you do it. Now, let's take a look at acetic acid as an extra example. So with acetic acid, I'm hoping that you recognize that there's the acetate ion right here, and this H plus can pop off, and if it does, it leaves behind the negative charges from these electrons, making the minus charge stick on this oxygen, and it becomes that tiny little particle of positive charge. Now if we have water around, that means it's going to be able to stick to that water molecule to make the hydronium ion and leaving behind your acetate ion. Now sometimes we just show it as acetic acid yields acetate ion and H plus. Other times we want to communicate that it's sticking to a water molecule and that it's definitely happening aqueously. You can write it either way, and it's going to be a correct way to write it. in almost all circumstances unless we've actually asked for something different.